Our next speaker is Nadia Loy from Politecnico di Torino, and she is going to tell us about cell reorientation under stretch.
Thank you very much for the kind introduction. And I would like to thank the organizers for this very interesting workshop and for giving me the opportunity of being here today. So I actually work in kinetic theory, not the classical one, so in kinetic theory for multi-agent systems. And in particular, one of my main research interests lies in cell migration. I don't want to give a methodological talk, but I would like you to give an overview of the methods which are used in kinetic theory in order to study biological phenomena. And in particular, I will use as a prototype problem the phenomenon of cell orientation under stretch. So first of all, just a brief introduction. So where's the origin? So the origin is the collisional Boltzmann equation. Oh, so I will have many formulas. I will go through everything. I won't give like the very details of everything, just want to give the general meaning of everything. So the origin is the Boltzmann equation, so which describes a gas as a set of molecules. So each molecule is identified to its velocity. So we have a velocity v and w of two molecules which interact in a binary sense, and after the collision they have new velocities v prime and w prime. So those collisions are ideal, so those are hard spheres, so everything is conserved and everything is fine. So we have this weak form of the Boltzmann equation. Here it's written in its very simplest and basic form. So we have f, it's the probability density function for the velocity v. Phi of v is the test function, so we have this weak form. Mu is the interaction of the binary collisions. And then we have this right term, which implements these interactions. So this is an integral partial differential equation, which is quite hard to handle. But it has good properties in this very simple case. So in particular, you have this conservation in each interaction of mass, velocity, and energy. Of course, this conservation also happens at the macroscopic level, and macroscopic quantities are introduced as statistical moments of the probability density function. So we have the mass, the average velocity, and the energy, which are defined as the 0, first, and second order moments of F. So the idea is to connect the individual states of the molecules to the macroscopic quantities. And what one can prove, starting from this collisional equation, is that its stationary equilibrium state is a Maxwellian, which is parameterized by the three macroscopic conserved quantities. Here E is the internal energy. What can be proved is that we also have a decay to this equilibrium, which is an asymptotic equilibrium through an H theorem and through this minus entropy functional. So I'm not going to talk about this, but how can this be translated for multi-agent system? So the idea here is that all the molecules are indistinguishable. And so this idea has been borrowed in order to model multi-agent systems in which agents are assumed to be that many so that they are indistinguishable and they follow all the same universal rules. So now V is not the velocity anymore. It might be a velocity, it might be a wealth, it might be an opinion. So it belongs to a general space V. And now our interaction rules are not the binary collisions anymore, but they can be expressed in this way. So we may have like a deterministic part, which depends on this interaction, and a fluctuation D, in which here eta and eta star are white noises, so with zero average and unitary variance. So the problem here is that a priori only the mass is conserved, and we have stochasticity, so we cannot determine the stationary state from this integral partial differential equation, so this Boltzmann-like, collision-like equation. So what can we do? So the idea is to study asymptotic states by means of the quasi-invariant limit. So the quasi-invariant limit, which actually comes from the grazing collisions of the Landau operator in classical kinetic theory, assumes to study very small interactions. So the new V prime velocity, wealth, or opinion is very close to the old one V. So here gamma is a very small parameter, and what you do is you observe these small interactions on a much slower tau time scale, which compensates for the smallness of the interactions. So on this slow time scale, you observe enough interactions in order to see the aggregate behavior. So what you can observe, what you can derive from this partial differential equation, integral partial differential equation in this regime is actually a Fokker-Planck equation, which is much easier to study. So just an, oh, it says that my connection is unstable. Okay, just an example. So a very popular example in the description of the exchange of wealth. So here V and W are positive wealths, is this kind of linear exchange interactions, which is based on a famous econophysics model from Chakraborty and Chakrabarty. So in this case, we have stochasticity, we have no conservation. So the idea was to consider this quasi-invariant regime, so to consider this slow time scale and slow and small exchanges. And if one performs the quasi-invariant limit, which we will see it later, amounts to considering Taylor expansion of this function about V prime, which is a small displacement with respect to V, then if we let gamma to 0, we obtain a Fokker-Planck equation. And for example, in this case, we can obtain the stationary state, which is a gamma inverse function, for which we can also find the Pareto index, which measures the thickness of the tails. So in this case, we have a fat tail distribution, which in this case allowed these authors to show that it might be that only few individuals hold a large amount of wealth. So what is the relation with respect to what, for example, Maria Rita showed yesterday, 2 days ago, sorry. So can we relate this approach, this collisional approach, to velocity jump processes? Well, yes, one can replace the collisional term here with transition probabilities. So we can write a transition probability which encodes the microscopic dynamics, the microscopic interaction. So we have the probability of going to V prime given V and W. In particular, the one that Maria showed you is this one. So she had the K operator here. And so you have this probability of moving from V to V prime. So what is the relation with the collision-like Boltzmann equation? So it can be shown that if you impose the same evolution of the moments of this equation and of the collision-like equation, then you have to choose this microscopic rule, and you have equivalence. So at least up to the second moment of the solution. And it is quite good. So this is almost banal, but how can we use this? We can consider a quasi-invariant limit for the transition probabilities. So we consider a small quasi-invariant transition probability in which we tend to stay according to this small parameter in the previous state. And if we impose this equivalence of the moments, then we find this quasi-invariant interaction rule. And by performing the quasi-invariant limit, then we can reach a Fokker-Planck equation. And this Fokker-Planck equation is equivalent in the sense of the 0, first, and second order moment to this velocity jump process. And this replies, I think, to the last question that maybe Jay did to Maria, who said, okay, Nadia is doing this. Yeah, okay. So the relation between the mean first passage time shown by Maria Rita comes from this equivalence between velocity jump processes and Fokker-Planck equations. Okay, so this was just a brief introduction on this kind of method for in kinetic theory for multi-agent systems. So what's the problem that I want to tackle now? So it's cell reorientation under cycling stretch. So this phenomenon is very important, for example, for cardiac tissues or for arteries. In general, in tissue engineering. So it corresponds on seeding cells on the extracellular matrix and on cycling, stretching the substrate. So what happens? So you may have essentially two scenarios. So in the first one here in the first row, so if you stretch your substrate, then you observe that your cells tend to dispose themselves in this way. So you will have these and these equilibrium orientations. Instead, if you start always from this random situation and then you stretch your substrate, but only in one direction. So here you're allowed to do like this and to compress also in the other direction. In the second situation, you're only allowed to stretch in the horizontal direction and you're blocked in the vertical direction. And what happens is that cells tend to reorient in the perpendicular direction to the solicitation. So the important quantities here are the frequency of this stretch and the strain tensor, which measures the displacement both in the horizontal and vertical direction. So you have this epsilon, which is the strain in the x direction. It is related to the one in the y direction through this biaxiality ratio, and all of these quantities can be measured. And this strain is cyclic. So you have this frequency here, which plays a very important role. So the point is that, of course, so you may find these equilibrium angles, orientations of the cells. Of course, they depend on the various parameters of the system. But then you have, of course, random.
A quick clarification question.
Yeah.
Is the stretching being done at that frequency? Why is there a time scale?
Why is there a time?
So you showed this omega, and I just didn't understand whether the stretching was being done at a certain frequency or just one time.
No, it keeps on going. It must keep on going.
Okay.
So if there's no frequency, nothing happens actually. So if you just do it once, they stay there. So you must keep on stretching. Yeah.
Thanks.
Like the heart, essentially. Yeah, sorry, I was not clear. So so if you look at the statistical distribution, you can get for various parameters different distribution of the orientation. So this is the case in which you can stretch in both directions. So you essentially have 4 possible equilibria. And so you observe your experiment in 0, 90 degrees. So what people have usually done is that they tend to describe the evolution of the orientation theta of cells according to this kind of ODE. So where E is an energy and the stationary state. So this distribution is given by this probability density function in which you have your energy, the Boltzmann constant, and a temperature. So we wanted to do, so in my group, we wanted to do something a bit more accurate. So we started to, some of my colleagues started from a mechanical description of this system. So what they wanted to do is to write a very accurate elastic energy, and in particular arguing on mechanical topics. They managed to model the evolution of the orientation of the cell in this way. So where here epsilon is your strain, lambda theta is the reorientation time of the cell, and then you have this mechanical energy bar U. This mechanical energy is very complex, but it essentially comes from a mechanical derivation, and it involves all the parameters of the system. So you have your biaxiality ratio, the strain coefficient, and there all the material coefficients which describe the response to stretching along the orientation direction, the perpendicular direction, and the response also to shear. So what did they do? They studied the stability of this mechanical energy, and they saw that this energy is actually minimized by the equilibrium positions. And they found the four scenarios. So essentially, you can have the 4 equilibrium positions, and also you can have the perpendicular equilibrium according to the direction of the single stretching direction. And when performing this stability analysis of the mechanical energy, they actually found compatible ranges of the parameters with respect to experiments in which these scenarios occur. Okay, but then they still had no they had no randomness, and they could not see how the frequency and the strain affected the distributions of the data. What can be observed is that so if omega is equal to 0, you have no reorientation, so nothing happens. But the distribution, if you look at the statistical distribution of your data, it largely depends on both the strain and on the frequency. So not only the equilibrium depends on epsilon, but also the broadness of this distribution. So in particular, what you can observe is that when increasing your strain, then you have more peaked distributions, and the same happens when increasing frequency. To this respect, there is also another important issue, that is the regime of low and high frequencies. So what they did in their mechanical study is they wrote a viscoelastic Maxwell-like model in the limit of high frequencies. So where here omega is your frequency and lambda is the viscoelastic relaxation time, which is pertinent to the cell. And they saw that when this quantity is small, then viscous effects dominate, and the effective reorientation times becomes this time. And you have transition from low to high frequency when omega is about in this range of the frequencies. Okay, so we wanted to include also these facts. So we introduced our probability density function, which has a pi, which is pi periodic, so it's positive, it's normalized to 1, and we impose to it these symmetry properties so that we can get the appropriate boundary conditions on the 0 pi interval. Then, okay, we said, okay, let us start from their differential equations. So we consider their strain, their cyclic strain, their mechanical energy. We have the evolution equation for F, the probability density function for this direction theta. In general, the actual experimental strain which is imposed is given by this relation, where epsilon is a mean strain over an oscillation period. So if we consider this constant average oscillation period, we have this evolution equation for F, and its stationary state is, of course, a delta. We wanted to go over this, and of course, what you can do, you add your noise, so you get your SDE, then you get your Ito process and your Fokker-Planck equation. So how does this Fokker-Planck behave well with respect to our data? Well, we took this and we non-dimensionalized it, so with respect to the reorientation time and to the strain, and we saw that this was our non-dimensionalized Fokker-Planck equation, where now the diffusive effect here is given by sigma, which is, sorry here, the noise in your SDE, divided by the strain. In the low frequency regime, where your effective reorientation time is given by this quantity, then we found this diffusive coefficient. So we actually found what we wanted in some sense. Now we see why. So first of all, we can study this equation, of course, so you can write it in flux form. You have your boundary conditions, which are periodic, and you can determine your stationary state, and you can also determine the trend to equilibrium through an H functional. So not starting from a collision-like equation, but for the Fokker-Planck equation. And so how does our stationary state behave? So we can compute it. It depends on this bar sigma, so on the sigma, on epsilon and omega, and on the mechanical energy. And according to the various parameters, so on the R and on the and on alpha, we can find the 4 scenarios that they found when studying the mechanical energy. But okay, what happens when we look at experimental data? So we consider experimental data, which give us almost everything. So we have epsilon, we have R, we have the parameter alpha, which comes from the analysis of the mechanical energy. And then we have a relation between these 2 mechanical parameters. So we only need to fix one, and we have this compatibility relation on these parameters. So eventually we have everything is given by the experiments, and we have only 2 free parameters. So this K tilde S and sigma, the one that we have actually introduced. So what we found when we compared to the histograms, to the data that I showed you before, was a quite good agreement. So in particular, when choosing this value for K, S, and varying sigma in such a way to match the average of their histograms and of our distributions, we had quite a good agreement between our stationary state, the purple line, and the histograms. So what happens with respect to the high and low frequency regimes? So we could also recover for a fixed value of a sigma the different results. So in black, we have our solution, and then their histograms. So here we have the high frequency regime, and here we have the low frequency regime. Then we looked also at the evolutionary behavior, and also when we consider a comparison with some experimental results, and we found a quite good agreement. But still, we were not happy enough because we wanted to include something which was more closely related to a microscopic process. Because what happens is that the cell, the mechanical energy may be quite accurate, but the cell doesn't know the mechanical elastic energy. So what we wanted to do was to start from an actual microscopic interaction rule. So we start from our collision-like Boltzmann equation, in which here we now consider this interaction rule. So here we have this drift, which is the deterministic. So after theta, the cell tends to reorient towards a theta prime. And then we have this noise, where here this is again a white noise. So the idea is if for every time step we can measure the reorientation angle, we could include this information here. So what can we do mathematically? So again, we can consider the quasi-invariant limit. So we rescale our the time and our microscopic rule. We consider the rescaled collision-like equation. Essentially, what we do is we perform a Taylor expansion of phi of theta prime about phi. And letting gamma to 0, we obtain this weak equation. And this by gaining the strong form, so integration by parts and the boundary conditions, which are dictated by the problem, yields us a Fokker-Planck equation. So what happens? Do we have a relation with respect to what we have done before? Well, yes, of course. So we can express this interaction rule, which is a discretized version of our SCDE. And if we perform, so here we have this small gamma parameter, which is, if you want, the small time step. So if we perform the quasi-invariant limit, then we obtain the same Fokker-Planck equation as before. So we are happy, but not happy enough. So we want to consider other rules. So how can we actually describe a more accurate microscopic process? So the idea is to consider reorientation as an optimal control problem. So we say that our theta prime comes from theta plus a small reorientation angle. That is the one which we would like one day to measure. So in this optimal control framework, we say that this is the minimum argument of an energy functional, which is given by this sort of kinetic energy plus this energy, which measures the distance between theta prime and a possible target. So the approach here is to write down a Lagrangian and the optimality conditions. So to solve this constrained problem. And this allows finding this optimal reorientation angle. So if this G distance is chosen again as our popular, famous elastic energy, then we can find this reorientation angle. We can write our interaction rule. We can add the noise, perform the quasi-invariant limit, and again, we find the same result. But again, the cell doesn't know how to measure this mechanical energy. So we introduce this G function, which measures the distance, again, between theta prime and the possible target. And we said, okay, how do I model the possible target? So I want that with equal probability, this possible target is one of the two equilibrium directions. So either the one in the first 0 pi half or the one in the pi half pi quadrant. So if we consider this rule, we can carry out the optimal control procedure. We found our optimal reorientation angle. We can write down the interaction rule, perform the quasi-invariant limit, and we find this Fokker-Planck equation. So again, we can non-dimensionalize this equation. We can find its stationary state, which is given by this function, where now, again, we have this sigma c, which is the noise. So the stochastic fluctuation divided by the strain. That is what we want. So those are, again, the same experimental data. We have in purple the old stationary state, and in green, the new stationary state. Well, it does behave a bit better. So we managed to recover better results in terms of the average and of the variance of the experiments. So what we wanted to test now is what happens in the transient. So what happens before these cells actually reach this equilibrium configuration. So we found some data, some time-dependent data. So in green here, you have the evolution of this average, so the cosine of 2 theta. And in red is a simulation of the time-dependent Fokker-Planck equation. So it quite matches well the data according to the confidence interval. So what have we seen? So we have seen how very classical methods of kinetic theory for determining the statistical description of can be used, in particular for describing the phenomenon of cell reorientation under stretch. And we have seen that, in particular, optimal control theory allows to describe an actual microscopic process because the cell, well, it minimizes a mechanical elastic energy, but it actually minimizes its individual cell. So now our perspectives is to perform new experiments. So we don't I'm a mathematician, so I don't do experiments, but we have found a collaboration with the University Federico II of Naples in order to validate this microscopic mechanism and to better understand the role of uncertainty and possibly of this optimal control mechanism. So I would like to thank you.
We have time for maybe one question. I'm curious about the role of that volume exclusion play in this. Like, I imagine this model, from my understanding, there's no sort of like volume taken into consideration for these cells when they're reoriented. So what is that?
You mean volume exclusion between cells?
Mm-hmm.
Well, in the experiments, they are quite far so that they don't actually interact. So this interaction rule that you express is only the orientation angle of the single cell. If you look at the experiment here, you see that they don't almost touch.
Sure, okay.
So yeah, you don't have, at this level, you don't need them. Then if you want to study an actual tissue, for example, the heart, then something should be considered.
Sure. Thank you. If there are more questions, we'll maybe take them during the coffee break. Let's thank Nadia again.